We'll be discussing reductions of degrees of freedom. That is, at moment-free ends of a structure, we can use the fact that we know that there's zero moment to reduce the size of the problem. Reduce the size of the stiffness matrix, reduce the size of the load vector, and simplify our work. We'll be applying this example to continuous beams, but the method can be applied generally, and we'll be using the direct assembly method that we covered in a previous video. We'll start by discussing some modifications to the previous approach. The first modification comes in our use of Appendix D. We'll be using these two entries instead of the entries that we've been using previously. What we see in each of these entries is that there's one end that's rigidly connected. These would represent the nodes that connect to the remainder of the structure. The other end is a moment-free end, and you'll notice that these two ends rotate naturally. The top diagram has applied a unit displacement of one end relative to the other, and the other has applied a unit rotation at the node that is connected to the rest of the structure. And for beams, what interests us most is the value of moment. 3EI over L squared for a unit displacement, and 3EI over L for a unit rotation. The other modification is in our fixed end forces. You'll notice once again that these diagrams are shown with one end fixed. This represents the node that connects to the remainder of the structure, and one end is a moment-free end. These are the diagrams for a uniform load or for a point load P, and what interests us most here is the value of F1. That is the moment at the node that connects to the rest of the structure. You'll notice that there's no moment at the moment-free ends because they're moment-free. So we already know that the moment there is zero. The last modification has to do with method 2 of force recovery. For method 2 of force recovery, we need to know the displacements and rotations at each end of the member. So as we solve the process, we will find a certain value of u that might represent the displacement relative between the 2 points or the rotation of the node that connects to the rest of the structure. And this second one is going to be much more common in continuous beams. In either case, if we know the value of u, we then know the value of the rotation as 3u over 2l. That's for the relative displacement. For the rotation of the node, if we know the value of u, we know the rotation at the other end is 1/2 of that rotation. Let's apply this concept in an example. This is a 2-span continuous beam. There's a uniform load over the left end. The left-hand node is rigidly supported. This is a little bit artificial, but I did so to just reduce the size of the problem so that we can focus on the new topic at hand. There's 1 degree of freedom. That's the rotation of the center node. The reduction of degrees of freedom comes in because we're not counting this degree of freedom right here. This is a moment-free end. We're not counting that degree of freedom. We'll just have to assemble our stiffness matrix and load vector differently and do the force recovery differently. In this example, we'll be using numerical values. W is 2 kips per feet. The length of each span is 30 feet. The material steel with a modulus of 29,000 KSI and a moment of inertia of 400 inches to the fourth. We'll apply a unit rotation at degree of freedom 1 to obtain the displaced shape shown. For the left-hand member, we have forces on the member and on the joint of 2EI over L and 4EI over L. I won't be going into detail about those because we've done that in a previous example. Let's focus on the right-hand side. Because the right-hand side of the right-hand member is a moment-free node, there's no moment shown on the member. Now, what is the value for the other moment? Let's look at the value from our appendix. This diagram shows a beam with one end being subjected to a unit rotation and the other end free to rotate. The value of the moment is 3EI over L, so we know then that the value of that moment is 3EI over L. We now look at the applied load. For the left-hand side, where there's the distributed load, the moment is WL squared over 12, which we've done previously. There's no loading on the right-hand side, so there's no force there. The next step will be to assemble the stiffness matrix and the load vector. I put matrix and vector in quotes because since there's only 1 degree of freedom, they're both scalars. Let's go through the direct assembly process. For the stiffness matrix, we'll keep track of our degree of freedom. K11 is the force at degree of freedom 1 due to unit rotation at degree of freedom 1. The total force on that node is 4 EI over L plus 3 EI over L, or 7 EI over L. The direction is opposite to the degree of freedom, so by our sign convention that's positive. So K11 is positive 7 EI over L. Looking at the applied load, the term P1 is the force at degree of freedom 1 due to the fixed end forces from the applied load. The value of the force at degree of freedom 1 is WL squared over 12. The direction is in the direction of the degree of freedom, so the sign is positive. Now this example doesn't show loading on the member with the moment-free end. This is something for the homework problem. So let's now solve for the unknown displacement at degree of freedom 1 and look at force recovery. These are the results that we previously determined, and we'll continue working from here. First, we solve for the unknown displacement as u equals k inverse p. Because these are scalars, k inverse is very simple. It's just the reciprocal, L over 7 EI multiplied by p gives us a displacement of WL cubed over 84 EI. Looking at force recovery, and we'll work with method 1, what we do is we take degree of freedom 1 times U1, and if we plug in numbers, we get the following values. Now here, I've had to recover the shears. We'll go over once more how I think about this. The moments on the left-hand member tend to rotate the member counterclockwise. So the shears have to form a couple that tends to rotate the member clockwise. That gives me the direction of the shears. For the magnitude, we'll take the 514 and the 1028, that's 1542, divide by the length of 30 feet, and that gives me the shear value that's shown there. On the other member, the applied moment tends to rotate the member counterclockwise. The shears need to be a force couple that tend to rotate it clockwise. That's how we get the directions. If we take the total magnitude of the counterclockwise moment of 771 divided by the length of 30, we get the shears shown there. We add to this result the result from the applied load. The diagram here shows numerical values, whereas the diagram on the left-hand side shows symbolic values. And the diagram on the right-hand side shows the shears. The load of 20 kips per feet times the length of 30 feet is 60 kips, divided evenly because of symmetry, 30 kips for each side. Add the two together, and we get the net member forces. So the moment on the left-hand side is 1800 plus 514. It gives us 2314. The shear on the left-hand side is 30 plus 4.2, gives us 34.2. The shear on the right-hand side is 30 minus 4.2, gives us 25.7. We carry the uniform load down. The moment on the right-hand side of the left member is 1028 minus 1800, which results in negative 771, which is exactly equal to the moment on the left-hand side of the right-hand member. So this serves as a check on our calculations. These two have to be equal because they're equal and opposite forces. The other two shears simply get carried down. So now we have our net member forces. Continuing the problem, we would then take these net member forces and find our shear and bending moment diagrams. Now these are presented here quickly. Obviously you can't do them this quickly, especially for the left-hand side member. These take some doing. This is an opportunity for you to try to reproduce these results on your own and make sure you know how to arrive at this result. Our last topic will be to see how the procedure changes for force recovery method number 2. In force recovery method number 2, we need to determine the displacements and rotations at the ends of each member. We'll start with our calculated value of our displacement vector u, which only has one term, which we previously calculated as WL cubed over 84 EI. That determines the rotation at the center node. So it tells us that the rotation at the center node is u1, and that applies to both members because both members are connected to the node at that point. The sign is positive because the degree of freedom was declared counterclockwise. Our value for u is positive, so the displacement is counterclockwise. The sign convention for method number 2 is upward positive, counterclockwise positive. Next, we'll consider the displacements and rotations due to our boundary conditions. The left end is a fixed end, 0 rotation, 0 displacement. At the center node, we have 0 displacement. That applies to both members that are connected at that node. On the right-hand node, we have 0 displacement. We still have one value that we haven't found, and that is the rotation at the right end of the right-hand member. Now, to obtain that, we'll look first at our displaced shape. We'll remind ourselves that this is a moment-free end that's free to rotate. The displacement U1 is applied at the center node. If we know the rotation at the node that's being rotated, the rotation at the moment-free node is half that value in absolute value. Now, the other aspect that we have to notice is the direction. U1 is counterclockwise. The rotation on the other end is clockwise. So it's that clockwise rotation that gives us the negative sign here. So we'll leave it here as an exercise for you at home to plug these values into the slope deflection equations, obtain the member forces, and make sure that you can arrive at these same net forces. With this, we have finished the topic of reduction of degrees of freedom. We've seen another example of direct assembly of the stiffness matrix and load vector. We've seen another example of both methods of force recovery, and we've finished applying the stiffness method to continuous beams.